Okay. Um, gonna start out or sort of gonna kick off with regression diagnostics. Okay. Um, does anybody have any prior experience sort of doing any regression diagnostic stuff? Yeah, William, what types of things were you focused on primarily with sort of the type of work you're doing?
Like the linear distributions, outliers,
Okay, so looking at linearity, outliers, and things along those lines.
how to approach it when essentially we had like, doing a lot of QQ plots to make sure
Yeah.
sort of the data follows the appropriate trend for using the linear regression.
Okay. Okay, cool. So a lot of this is going to be stuff that you've kind of sort of heard and sort of seen about. You could have multiple courses just on regression diagnostics alone. There's just so much out there in terms of going through and trying to go through, find, identify, see if things are meeting sort of the underlying assumptions of our model. There are lots and lots of other statistics to go through and do. There's lots of sort of approaches and ideas on how to go through and do things. This is me sort of going through literature and thinking about for um, applied work in behavioral sciences, some things that are sort of good to go through and sort of think about in other domains and disciplines, right? Even within behavioral sciences, you'll hear, so I think we mentioned last time, think about censored data, right? Or sort of, or Windsorized data and sort of cutting things off. There's just lots of different ways to go through and approach this. This is sort of should give you a handful of tools that cover most of your bases. So if you ever sort of go through and need to do some additional things, you should have some foundation. This is also, I think the trick here with these is trying to determine, like, one, at what point do I identify something that needs to be addressed? And so what stuff is not optimal, but things that I don't need to mess around with, right? Like any type of analytic model, right? Thinking about parsimony versus complexity. Complex fancy models are real exciting, and so doing all sorts of fun diagnostics is fun, but then you have to explain what you did to reviewers in a way that doesn't make it look like you were just like throwing out cases that you didn't like, right? So just really understand what's going on, why you're doing things, and what the potential impacts of violations are starts to become really, really important. Okay, and so we'll focus on that here. Okay. So thinking about our basic regression assumptions, okay, with our model, what are the things that we're assuming in order to have strong interpretations of our results? Okay, first thing we need to be thinking about, and sort of this is formal, just statistical theory. We're assuming that predictors are fixed, non-random variables measured without error with variance greater than zero. Okay, there's a lot of stuff packed into there. Okay. Two, we're going to assume that our errors are normally distributed. This starts to be critical. We're going to go through, we're going to screen for our observed variables, but really mostly what we're worried about in regression is what's going on with our residuals. Okay. Our residuals, these are our errors, right? You'll see these indicated as E sub I. This is just the error term for Jack, the error term for Jayla. Here's what my regression model predicted for Cindy. This is how far we're off in terms of what she actually reported versus what the model predicted. Okay. Always, always, always to remember that anything that we have predicted in a regression model is a predicted outcome. It's not real life. It's just what this model predicts. And the distance between, on average, what we're predicting and what we're actually observing, that starts to tell us the quality of our regression model. If we're real close, our R squared is going to be pretty high. If we're way far off consistently, our R squared is going to be pretty low. We also are assuming that the variance of our errors are consistent for all values of X. Okay. So for any value of my predictor, I'm assuming that my errors have a constant variance. Okay. This gets into our homoscedasticity assumption, right? We're looking at the conditional distribution of our errors based on every single value of our predictor, and we want the variability, the extent to which our errors are jumping, are distributed on that regression line to be evenly spaced. We don't want skewed residuals. That starts to cause problems. Okay. Or unequal variances, that gets into our heteroscedasticity. Our errors are assumed to be independent. Okay. What we're saying is that here, how far I miss in my regression model with Katie should be unrelated to how far I miss for Cindy. It's unrelated to how far I miss for Catherine, right? Our errors are assumed to be independent. And then here, what we're also assuming is that our errors are uncorrelated with our observed values of X. Okay. This says that, Jack, in your thesis model, that the extent to which your prediction is off is not related to any of your observed variables. Okay. This is not something that we can actually test. This is by definition true with OLS regression, but we're making an assumption about sort of real life and what's going on with things. We're also going to go through and we're assuming that the error, expected value of error in the population is 0. Okay. We're saying that if we were to go through and run this model in the actual population, on average, our errors would converge to 0 across things. Okay. These last two aren't things that we can test directly. These are assumptions that we have to make. If we violate those assumptions, sort of, it maybe isn't the end of the world, but things we need to be thinking about with the stuff. Okay. So these are our basic assumptions. Okay. If I have a model that meets assumption 1 and then 3, 4, 5, and 6, what I get is my best linear unbiased estimates. My estimates are blue, meaning that sort of things are working out sort of pretty well with things here. Okay. If my residuals are homoscedastic and independent of one another, we'll refer to this as my residuals being independently identically distributed. IID, you'll see this in methods literature. So this is what this is referring to. Normality of my errors are required for unbiased estimation of my standard errors. Okay. And again, we've talked about this. Most of the consequences of violating my assumptions will not necessarily be for my estimates, although that can happen. Most of the time, it's going to be my standard errors aren't correct. And Catherine, when my standard errors aren't correct, what happens?
It messes with the test statistic.
It messes with my statistics, right? That p-value we're all really interested in looking at and interpreting, that starts to get thrown off if I haven't met my assumptions. A lot of times we violate assumptions. My sort of point estimate is just fine. It's just my test of those estimates start to get thrown off, right? Which sometimes may or may not be a huge issue, but if we start looking at things like around that 0.045 or like 0.053, right? There's uncertainty there that sort of starts to impact on performance. Okay. So again, as I'm going through and I'm starting to find violations of my assumptions, two things that I'm primarily concerned about. What's going on with my estimates of my population regression coefficients? Is the estimates that I'm pulling from my data representative of the theoretical coefficients sort of that are out there? Okay. Am I biased in any sort of way? Other thing that I'm concerned about if I start to violate assumptions, what's happening to my standard errors and my mean squared residuals? My standard errors for my regression coefficients, that these are going to be involved in the test of whether or not my specific predictor shows a unique association with my outcome, right? These are my individual regression coefficients. My mean squared residuals, we tend to worry about this less because this is your test of your R squared, your overall model test. And in psychological science, we often won't worry about that. We should probably worry about it a little bit more. So maybe I'm less worried about that. But for our purposes, we're often focused on sort of these individual predictors. And if I violate assumptions and my standard errors get wonky, that starts to create some difficulties. Questions? So these two things are just terms, right? If you see that someone's reporting that their regression was blue, that means it's their best linear unbiased estimates. They're talking about residuals being independently identically distributed. They're just talking about these are just callbacks to different different assumptions in your regression model. Okay. So, this All right, enough playtime. Go away. Okay. Okay, cool. So let's start tackling these one at a time, talking about what this actually means. So your fixed effects assumption, your first assumption of regression is that your predictor variables are fixed, non-random variables measured without error with variance greater than 0. Okay, this is actually a lot of assumptions kind of all packed into one. Okay, first thing we're talking about here is a fixed effects non-random, this idea of a fixed effects model, non-random variables. Okay, fixed effects model assumes if I've specified a fixed effects model, what this is saying is that the predictors that I've selected are not random. Okay, and not random. I just randomly selected some things. The values, the responses that I'm getting are not random. They're fixed. Okay. We're saying that for the variables that are included as predictors in my model, what I've done is I've systematically gone through and sampled so that all possible responses of interest within my model are captured, that any possible replications that could be done with this, all of these things are gone through and collected. Okay. So let's say, Charlotte, you're going through and what is your predictor?
Adverse childhood experiences.
So,
Adverse childhood
okay,
experiences.
adverse childhood experiences. If you were going to run a mixed model or a fixed effects regression model, what that would mean is for adverse childhood experiences, however you're measuring this, all possible values that would be relevant to your population of interest are captured and recorded within the content or within your sample, right? So let's say this is, and this is a really good example because I don't even know how this would work, right? Because the adverse childhood experiences are you talking about like all possible childhood experiences that would ever be relevant or interesting to sort of your question are captured and reasonably represented within your sample? Is it if you have a scale, so you've got a 1 to 50 scale of childhood diversity, every single possible point, so the value that someone could get on that scale is all collected and represented within this sample. The idea of a fixed effects model is that no one could ever go, all values that I have for this predictor that could ever be of interest for this particular question in population are represented within my sample, okay? If I'm going through and doing this, is that, would I expect a normal distribution of these scores? Nope. What I've done here is I've gone through and I've said, let's say, Kitty, you're running an experiment. This is where we actually can do this, right? Like let's say you're running an actual experiment, like a proper randomized experiment. And what you've done is you've randomized people to all three conditions that would ever be of interest or use in sort of predicting some outcome, right? So you got people in condition 1, condition 2, condition 3. For this specific question, there's no other conditions that could be of use. And you systematically randomly assign sort of 10 people to this condition, 10 people to this condition, 10 people to this condition. That's a fixed effects model, right? Whereas Charlotte's, so here you're going through and you're pulling specific colors out, and so everything is equally distributed or equally represented. Charlotte's study, however, if I'm looking at adverse childhood experiences, how do we run that, right? We certainly don't bring people up and assign them to adverse childhood experiences. That's wildly unethical, right? And we're probably not going to go through and like ask people like, how many of you had, now you're out or you're in. What we're doing is we're inviting people into our study, and then whatever distribution of that predictor we get is what we're working in, okay? This is a random effects model, right? But our standard regression model assumes a fixed effects model where everything is equally sort of captured and represented, right? So with our fixed effects regression, what we see is we have no assumptions, distributional assumptions of our predictors, okay? Kitty, in your hypothetical experiment, if condition is a predictor in your model, what is the distribution of your categorical prediction or your categorical condition variable? Is it normally distributed? Yeah, so for, let's say you've got condition 1, 2, and 3. If you're looking at the distribution of condition, is condition normally distributed in that?
If it's randomized, yes.
Well, if it's well, the outcome might be sort of, whatever you're measuring on the outcome, that might be, have a normal distribution. Is your predictor? No, right? You probably got a square distribution where you've got sort of condition 1, condition 2, condition 3. Now it's a categorical variable, wouldn't necessarily sort of interpret a distribution about that, but like you've systematically sampled and put people, randomized people to certain conditions, and these are all the conditions that you're interested in. That's a fixed effects model, okay? Same thing, William, if you went through and you said, okay, so I'm interested in something looking at people who are taking anywhere from 0 to 20, drinking 0 to 20 drinks a week. And so then you go through and you find undergrads and so you specifically select people who have taken 0 a week, 1 a week, 2 a week, 3 a week, 4 a week, 5 a week, so that all of these are included in your sample. Are you gonna end up with a nice normal distribution of your predictor variable? Nope, it's gonna be square, right? Because you've got sort of the same number of people for each one. This is our fixed effects regression, okay? And with a fixed effects regression, so then we don't make any assumptions about the predictors of our, or about the distributions of our variables, because we've got all possible values of that predictor covered in the model, okay? Is this how we run regression outside of experiments? No, it's for sure not, right? We're doing what Charlotte is doing and going through, and we invite a sample in, and then whatever values of that predictor variable we have is what we go through and work with, okay? So this, though, is a random effects regression. This is not what we're assuming under our basic assumptions here, okay? So again, this fixed effects assumption almost always violated in practice, okay? So right off the bat, basically, someone handed me a chisel and I'm using it as a pry bar right off the bat, right? Like I'm not using this in the way it's intended or was developed to be used, but that's all right. That chisel can still be a pretty good pry bar under certain circumstances, right? And so for our regression models, what we're assuming is, what we know is, even though we violate this fixed effects model, we're okay so long as our predictor variables are multivariate normal. Okay. So from a classic regression, from a theory-based standpoint, we don't have any assumptions about about the distribution of our assumptions, distributional assumptions of our predictor. But because we're not running fixed effects models, we're actually running random effects models, we can still run our regression like we normally would. Well, now what we take on an assumption that our predictors are multivariate normal. So now all of a sudden we need to go through and start thinking about sort of our distributions here. Do people kind of understand this and kind of what we're talking about? Okay. In your handouts, there's a review that I wrote for a journal submission. Someone well-intentioned had picked up this idea that for our regression model, there are no distributional assumptions for our predictors. And sort of got excited about the fact that when we're reading good research papers, people are generally talking about the prediction or the distributions of their variables, and wrote a whole review paper about how this wasn't necessary because regression models don't have assumptions about the distribution of variables, and like pulled a bunch of papers and was like tallying up how many papers had gone through and like talking about distributional assumptions, when for a standard regression it wasn't that. With those, technically you don't have those, right? And so for this review, I had to write yes, and because in practice we're always violating this, and because we violate that in order to produce unbiased estimates, we now do have to make sure that things are multivariate normal. So yes, people are doing this, and probably understand, like reasonably so, because of, yeah, we can violate this, but if we violate this, then we have an added burden of multivariate normality in terms of our predictors, and that's why this is going. So again, sort of put that, try to gently sort of explain sort of the fundamental issue with the paper, to write that out, but it also kind of doubles as a nice kind of summary of sort of this piece of things. do people understand conceptually what's going on and why then we have to be concerned with the distribution of our predictors in order to generate unbiased estimates from these models? Okay. All right, so this covers the fixed effects non-random piece of things, okay? We're also assuming within standard regression assumptions that our independent variables, our predictors, are measured without error. Jack, do we ever do this? Nope, we sure don't, right? So we're 0 for 2 on the components of this first assumption, right? Basic measurement theory, classic measurement theory says that any true score or any score that I observe, that I measure, right, is going to be a combination of the actual sort of latent true score and then some error, right? So I've got with my measures some sort of component of the actual construct that I'm interested in, plus some measurement variability. Okay. When we're thinking about measurement error, if I've got measurement error in my outcome, okay, it doesn't bias my parameters, but what it does is it relates to inflated standard errors. Okay, if I've got some outcome variable that's really, really tight in terms of measurement, that's awesome. That's going to shrink up my standard errors. And again, sort of making an argument for sort of stuff that you're all talking with Kyle in terms of methods. Methods and statistics go hand in hand. This is why it is important to go through and choose psychometrically sound measures. So what we're doing is we're reducing that error. We're getting closer and closer in theory to sort of capturing more true error variance as opposed to error variance. And when we do that, we start to reduce standard, if we get that in our Y variable, or outcome, we start to shrink up our standard errors. And if we shrink up our standard errors, Catherine, what happens to our tests? They get bigger, right? This is beneficial to us to go through and have good measures, right? Problem is though, is that we have measurement error in our predictors. This does start to result in bias parameter estimates, okay? If we go through and we think about sort of by given x, this is our regression coefficient here, okay? And based on classical test theory, my estimate of this regression coefficient is going to be a combination of the true population coefficient multiplied by this reliability estimate. Okay. Someone tell me what's the range of reliability estimates? You can think of anything. They sort of coefficient alpha, let's say. What is coefficient alpha range from internal consistency estimates? What's the real range of a reliability estimate? I think, William.
Like a Chromebox,
Yeah,
like 0 to 99 or something.
yeah, 0 to 1, right?
Yeah.
0 meaning absolutely no reliability, 1 meaning perfect reliability. Okay. We're doing basic algebra. If my observed coefficient is the product of the population effect multiplied by my reliability, under what conditions is my population estimate unbiased? Only when this value is 1, okay? If this value is less than 1, what happens to a number if I multiply it by a decimal? It goes down, right? So the problem is, the reason why our assumption is that our predictor variables are measured without error is as soon as I start introducing error into the measurement of my predictors, what does that do to the estimate of my estimate of the population coefficient? It shrinks it down and makes it too small. My regression coefficients themselves start to become attenuated. Okay, so if I have measurement error in my outcome, it's not great. But what it does is it messes with my standard errors, makes them too big, and so then it makes for a more conservative test of my individual predictors. If I have error in my predictors, though, this is biasing the actual estimate, the actual coefficient for my predictor, and it's making it too small. As this error term, or as this reliability term decreases, it gets smaller and smaller and smaller. What happens to my corresponding estimate of the population coefficient, Katie?
Sorry.
It gets smaller and smaller. It shrinks, right? So now all of a sudden, I've got something like, well, I don't have evidence for an effective X on Y, when maybe I just have a really, really dirty measurement of X, right? I didn't go through and I didn't get a good psychometrically sound measurement or measure of this thing. I just kind of made something up with unknown psychometric properties. So I got a ton of error in this. what did I just do? I just screwed myself because now I've attenuated that association. It's not as big as it should. Okay. And so if we're trying to get unbiased estimates of our regression coefficients, error in my predictors does start to create bias that starts to become problematic. Can we do anything about this? Can we measure our fuzzy psychological constructs without error? No, we can't, right? This is just kind of baked in, right? But what we can do is start thinking about with our research, making sure that we're pulling psychometrically strong measurements, things that have evidence for interpretability, validity, reliability, because what it's doing is it's going to go through and this will never be perfect, but we're at least minimizing the potential for bias in my estimates if I've got psychometrically sound sound measures. Okay, there's no real test for this outside of like sort of reporting your reliability coefficients of your measures, but if you see something with really poor reliability, not just because like, oh, it's bad because it's less than 0.8, right? It's problematic because it's probably attenuating sort of the effects that you're likely to get in that research. Questions? Is this making some sense? Okay. So assumption one is a co-compatible watch because like we started out, first of all, we violated fixed effects assumption, and so then that's out. We're measuring everything with error because it's psychological science, and so then we've got that issue to deal with. And then variance greater than 0, what does that mean? Why do I need to have variance greater than 0? Yeah.
Mean that it's a variable.
Yeah, because otherwise I got a constant and I can't, it'll crash my model. So it just, scores are different to some extent on things. Okay. Okay. Second assumption is that we have errors that are normally distributed. Okay. This starts to become important for tests of significance and for tests of significance for your R squared and your regression coefficients. Okay. What we're assuming here is that we have homoscedastic errors. So if we're going through in a very simple regression here with X on the X-axis, Y on the Y here, here's my regression model. For any given value of X that I would choose, the distribution of errors around that are going to be roughly the same. Okay. If I have something that looks like this, then I would say that my errors are homoscedastic. And we'll get into our normality assumption. If most of them are stacked up really kind of close to this line and then sort of slowly spread out, we're going to assume that they're also normal as well. Okay. If I have non-normal errors, there can be a number of different reasons that this can be true. Okay. And it usually ends up sort of, or it often ends up being sort of a function of ceiling and floor effects. And these are not examples that I sort of came up with organically. These are things from textbooks. So overly sampling severely depressed individuals or heroin use in children. That's sort of a dark and weird kind of one, but we're going through and thinking about what this would look like. Okay. If let's say that I'm going through and I'm looking at the relation between depression and life satisfaction. Well, what I've done is I've only sampled severely depressed individuals. Okay. What I've got is a bunch of people who are severely depressed. I've got a truncated range, right? I've only got sort of the high end of depression. And so I've got variability, but I've just got sort of our most severely depressed people, right? Jayla, if someone is severely depressed, what's their life satisfaction likely to be? Really low, right? And so when I look at this regression model, almost everybody is stacking up down on this floor, okay? So if I'm gonna miss anywhere, right, and so like say, here's what my model is predicting, but my error is way off, what direction does that error go, Katie? In this model here.
You repeat that, sorry.
Yeah. So I'm saying, here my regression model, just because everybody is really depressed, no one is doing well. And I've only looked at like super severe individuals. So across the range of depression that I have measured, no one's doing well. But if I miss, if I have an error, where did I miss? So my prediction model says life satisfaction should be close to 0. And if I have a miss, where does that miss by definition have to come then?
My understanding.
Can I miss low? No, I can't because I've already floored out. There's nowhere, my model is already predicting the lowest value, so I can't predict any lower than the lowest value. So if I miss, where am I missing? I'm missing high up here, right? So because it is possible for maybe I have someone who has struggles with a lot of, there's probably not going to happen a whole lot. Someone who's struggling with a lot of depression could maybe say like, yeah, I'm sort of struggling, but overall, so I'm satisfied with my life in other areas, things along those lines. So you got people who are actually sort of kind of hanging out here, not a whole lot, right? Well, what I've done is I've hit a floor effect. The only way for me for my regression model to miss is to underpredict life satisfaction, because here's the floor. I can't get any farther down than that. So I can't miss in the negative direction. I can only miss in the positive direction here. Okay. Same thing if I go through. So again, so we get a floor effect here. When my regression model is wrong, my outcomes are systematically exceeding my predicted values. You're kind of seeing how this is happening. And then, Jack, if I'm going through and like looking at the distribution of these residuals for any given value of X, what does the distribution of these residuals look like?
Like positively skewed.
Positively skewed. They're all kind of packed up around my regression line, but instead of being like a nice normal distribution, when they're sort of extreme errors, they're all in the positive direction. So I've got positive skew to all of this stuff. Same thing with this other example, sort of looking at sort of age and heroin use, right? And hopefully small children aren't using the heroin, right? And so as age increases, like sort of heroin use is probably going to be very low, right? So again, the same thing is like no one's using heroin, but if I miss on no one using heroin, where do I miss? People using heroin, because you can't use negative amounts of heroin because that's kind of the lowest we can go, right? So yes, probably not a lot, but like we may go through and find higher levels of use in people, but my model's not going to predict that. My model is going to predict everybody is using next to 0. And so if I miss, it's always going to be in one direction, which is going to give me skewed residuals like this. Okay. This is a little bit tricky. Do people see sort of where for any given value of my predictor, what I'm doing is I'm looking at sort of the distribution of those residuals. They're all packed around here, my regression line. But when I miss or when there's errors, they tend to be going one way. People kind of see this? Okay. A lot of this will need to be thinking about omitted variables and ceiling and floors effects with things. So what happens if I violate this normality assumption of my residuals? Okay. Regression and coefficients are unaffected. Like my actual coefficients corresponding beta weights, these are all fine. But what it's going to do is it's going to depress my standard errors. Okay. And if I have a small sample of non-normality, it's going to suppress the standard error of my R squared. Okay. Now we already have concerns about with the small sample, my R squared value being too high. It's like with small samples, we expect correlations to be too big. If I then have to also build in non-normal errors to this, not only is my estimate of R squared too big, now my standard error is too small. So then I just have this massive p-value that's not warranted because my estimate's too big, my standard error is too small. We kind of get double duty here. In general, though, if I have non-normal errors here, what's going to happen is it's going to shrink up my standard error. And then I'm going to make more type 1 errors than my model would suggest because my standard error is too small. T-tests are going to be too big. And I'm going to be claiming unique effects of individual predictors when it probably shouldn't be. Is this making some sense? All right. Third assumption. We're assuming a variance of our errors is constant for all values of X. Okay. This is similar to our homoscedasticity assumption that we talked about previously, right? When we were going through and we're talking about the correlation of X and Y, right? We're talking about one is seeing these scatter plots showing evidence of homoscedasticity. So what I don't want to see is something that like something that what I want to see is that around my regression line, my sort of values are sort of not skewed one way or the next, right? So it's a constant variance across the whole range as opposed to really tight and spreading out. Okay. Same thing here. It's just we're thinking about our variability of our residuals. Okay. So again, going back to this plot here, this is really nice. What I have is normally an identically distributed residuals. My residuals are IID here because they are here to be relatively normal in that they sort of kind of stacked up. Sort of my errors tend to be pretty close to that regression line, and then sort of get sort of spread out. And then also across any given value of X, variability is pretty constant in terms of these scores across the whole level. People understanding sort of this homoscedasticity assumption. And this is not different than homogeneity of variance we talked about in our grouping in our last year with like t-tests and ANOVAs. Here, my group, right? Group one, group two equal variances. Same thing here. It's just we're taking sort of one group and turning that into infinite groups. And across those infinite groups, my variability and my outcome should be the same across all of these. Here, we're just talking about this in terms of errors. When I see heteroscedastic errors, this can be a product of measurement error. Okay. If I'm looking at sort of IQ and achievement, and again, we talked about this a little bit last time. Charlotte, as we get to the upper and lower extremes of IQ assessment, what happens to the reliability of my scores? What's that? It decreases, right? And so what I might find with this is if IQ is my predictor and achievement is my outcome, what I might find is for people who are I'm less good or I have more variability in my prediction for people who are very on the very, very high end of the scale, very, very low end of the scale, because my measurement starts to get worse there, right? So I've got more variability as opposed to the center of the distribution. Okay. Other thing that can happen too here is if I'm seeing heteroscedasticity in my residuals, what I would start thinking about is whether or not I've got if I'm missing a predictor in there. Okay. So let's say, Jack, I'm looking at the relation between age and income. Why would I expect heteroscedasticity in my errors for if I'm looking at the relation, if I'm regressing income onto age?
Like there's other predictors affecting income that are associated with age, like education level, that kind of stuff.
So what I might find is for people who are 18, 19, 20, prediction's pretty good. Variability is not sort of really all that much there. But as I go through and follow people development and off in the lives, sort of 30s, 40s, 50s, 60s, I'm still sort of got my regression line. I'm still predicting, but I got a lot more variability. I miss more often at the high end of age than I do at the low end of age, right? Well, what might start to account for some of that additional things? Probably education, right? As people get older, sort of what's their level of education? And if I go through and I control for education, now all of a sudden what I might see is the regressions or my residuals for the prediction of income based on age start to become normal. Once I account for education levels, then I still get the same variability across the whole length of my regression line as opposed to if I have that omitted. Okay. So if we're going through and we're doing screening, if you're saying you've got heteroscedastic residuals, you should start wondering, am I missing something? Is there something that needs to be in my model that I have forgot or have omitted, right? Again, it starts to get back to, as we're going through and doing this, not just saying like, oh, there's a problem. Think about what is the problem and what does this tell me about my model, the question at hand, things along those lines. This is where knowing your content area starts to become critical, right? Because there's no test. I can't run a t-test on whether or not I need to have covariate for age or any other such thing, right? That requires you to go through and think about like, what's the thing that could be driving, like, why is variability in my prediction getting bigger and bigger and bigger as my sort of variable starts to increase? That's a conceptual question that hopefully you're able to go through and think carefully on. Questions about this? Okay. What happens if I don't have homoscedastic residuals? Well, again, regression coefficients remain unbiased. My b-values are fine. No worry there. But again, standard error estimates are biased, this time in the direction of the relation of the errors to the predictor. Okay. A couple of different things that can happen. If I've got a fanning out pattern where variability in my residuals gets bigger as my predictor increases, right? I've got a fan out kind of packet or thing here. What it's going to do is it's going to depress my standard errors. My standard error is going to be too small, and so I'm going to have too liberal of tests. Alternatively, if my error variance decreases as my predictor increases, here I got kind of a funnel shape where they're real big at the low end and they sort of shrink down as things get bigger. Here, what I'm going to do is I'm going to inflate my standard errors, and then I'm going to have two conservative tests. I'm going to make more type 2 errors that are sort of more type 2 errors than sort of what is implied by my test. So kind of seeing like, so we really start to become really hyper focused on what our residuals are doing within these models. Okay. Questions about this? So, and again, wanting you to sort of be thinking about this and picking things up, because this can start to become really helpful in terms of interpreting what's happening, right? So, Cindy, let's say you're running a regression model and you're finding things are kind of marginal, right? But you notice in your screening that you've got sort of this kind of funnel-shaped pattern of your residual. You got heteroscedasticity in there. You're like, well, probably what's going on is I've got a inflated standard errors because I've got this violation of my assumption, which is probably maybe leading me to tip one way towards an interpretation as opposed to the other. All right. Assumption. Errors are assumed to be independent of one another. Okay. If I have dependency in my residuals, we're talking about this as, we refer to this as autocorrelation. Okay. Different types of autocorrelation that we can see. Okay. If I'm doing, Jay, let's say you're doing some longitudinal types of analyses, right? Where you're looking at sort of measuring the same group of people repeatedly over time. What we might find is that observations that are happening closer in time start to become, those errors start to become more strongly related than observations, the sort of missing that we're getting and stuff happening farther away. Okay, what we have here is temporal autocorrelation. Okay, the assumption of regression is that my errors are independent of one another. But if I'm measuring William at time 1, time 2, time 3, time 4, time 5, is it likely that sort of error or Williams, how far I'm missing on William starts to become kind of consistent across time points? Yep. And that sort of those misses that are occurring closer in time are more tightly correlated than things farther away in time. Yep. So we got correlated errors that are a function of my methods here. This repeat measure approach. Okay. I can also start to see situations where I have correlated errors due to observations being pulled from individuals sharing a similar environment. Here we've got spatial autocorrelation. So let's say, Charlotte, you're doing something in schools, you're working with kids, right? You've gone through and you've got sort of participation from a number of different school districts, a number of different buildings where you're going to go in and sort of measure, sort of like observe kids on some sort of outcome and things along those lines, right? Would I expect that all kids taken from all classrooms, taken from all schools are going to be completely independent of one another? Probably not, right? Because probably if everybody is sitting in Miss Smith's class, is probably going to have a lot of the same types of things going on than everybody in Miss Jones' class versus Mr. Brown's class in a different school in a different area, right? What we have is that we have a group of individuals who are not independent of one another. They are, no one's like looking over each other's shoulder, but they share a common environment. And so what we're starting to see is spatial autocorrelation here due to a nested data structure, right? Here, what we're seeing is that any two individuals sampled within this individual classroom are likely to be more similar than any sort of random individual scheduled sampled from two different classrooms. Okay, and because we have a factor there, a structural factor that's creating maybe not huge, but a closer association of errors based on where we sampled them from. Now we've got a different problem with autocorrelation here. And this is what we would sort of typically start talking about in terms of nested data structures. Okay. Let's say, Jayla, you're doing a jury study, right? So you're like, oh, I'm just going to like regress individuals' responses, even though they're grouped in juries. Well, so everybody in this jury probably going to have similar influences than someone from a different jury. And so now any two people from the same jury are probably going to be more similar than any person across juries. We've got a violation of our assumptions here because we're likely to have correlated errors from things. People see the issues that happen here with when we have non-independent errors and structurally how this sort of tends to come up. Again, if I have correlated errors, regression coefficients are unaffected, but my variance estimates are going to be biased. My mean squared error and my standard error of my individual regression coefficients may be substantially underestimated. Has anybody done sort of work or in their lab or sort of anything like that with multi-level modeling stuff? Higher level things. Multi-level models are sort of developed to address just this, right? The idea is either if I've got a longitudinal multi-level model, right? What's going on is I'm measuring the same group of people over time, sort of EMA types of stuff or things along those lines. We're going to have temporal autocorrelation where people's errors are sort of within the individuals associated with one another. If I just ignore that and just run a straight OLS regression, what's going to happen? My mean squared error, my standard error, going to be way too small. Everything's going to pop up as statistically significant when it shouldn't be. It's a side effect of sort of the violation of assumptions here. Same thing anytime you say school-based, sort of classroom-based stuff, always going to be using a multi-level model. If they're not, that should raise a big red flag because what's going to happen is the kids in individual classrooms are going to be more similar to one another than they are to kids in other classrooms. You got spatial autocorrelation. What those multi-level models do is they go through and they separate things into within between group variability and model that appropriately so that we get appropriate errors, estimates of our standard error and sort of appropriate tests of our individual effects. Questions about this? So this isn't something that I mean, there are things you can do to try and go through and kind of test some of this stuff. We're not going to worry about that so much. We're going to focus primarily on what was the method, how are these data collected? Is there any reason that I might be worried about any sort of autocorrelation types of things? Questions here? Okay, independent errors. Here, and this is something that we just have to assume that we can't actually test statistically. We're assuming that my errors are uncorrelated with my observed values of X, right? We're saying that how far I'm off in terms of my prediction is not related to the actual value of my predictor, okay? Uncorrelated observations and errors are correct, are a product of correct specification of my regression model, okay? When we're talking about correct specification, we're saying my model, whatever I'm trying to predict is my model is correctly specified if all my relevant predictors are included, all my irrelevant predictors are not in there, and the form of my relation is correctly specified. Thinking about your own research areas and sort of the types of things that you're interested in studying. How often is it, do you think, that we have truly properly specified models in terms of our standard regression stuff? Probably never, right? And we're all guilty of this. I have these data. I'm interested in predicting this outcome. Here's some predictors I think should be sort of included in here and stuff like that. So I go through and run it. If my outcome is PTSD, did I include all things theoretically, conceptually, empirically that we know should influence PTSD? No, I didn't include all those things, right? Is it reasonable for me to do that? Probably not. But is it a violation probably of model specification? Yeah, probably, right? Now, there are reasons why I might strive to go through and include a proper number of predictors, right? And to get most things in there, what that's going to do is it's going to increase my R squared value. And if my R squared value increases, what happens? My mean squared error decreases. My mean squared decreases, my standard errors are going to decrease, right? You give them more power if I've got a good model that's accounting for things. But in terms of model specification and sort of this, we've probably got issues going on. Okay. Other thing too, okay. Let's say, Catherine, you're running a model, right? And you're like, okay, well, I'm going to go through and I'm going to run this regression model. And I've got through, because this is for your thesis, right? And you're saying, like, I've got these 5 predictors in there based on the literature. I'm going to go through and run this model. And then when I run the model, I find that predictors 1 and 3 aren't coming up as statistically significant. And so I'm saying they're not contributing the model, and therefore I'm going to pull them out and rerun the model so that just has the ones, the predictors that are coming up as significant in there. I understand why you did that. Should you have done that? Probably not, because there was probably a reason you had those other 2 predictors in there in the first place, either theoretical reasons, conceptual reasons. And if those predictors were good enough to have in there in the first place, even if they're not in this sample coming up as statistically significant, or model specification, right? These are in there for a reason because they help us, so we have a reason to believe that these are helping understand this phenomenon of interest. Whether in a p-value sort of cracks a 0.05 level or not, starts to become irrelevant, right? And what we're talking about is trying to have a correctly specified model here. This is one of the things that starts to become problematic with sort of overly empirically driven approaches to analysis. Say, sure, for your data, this thing didn't contribute, but that probably shouldn't trump a whole literature that says, like, yeah, in general, this thing tends to be associated with that outcome, right? What we can start to do is we can start to cut models down to be very, very sample specific and don't actually generalize anything outside of like your set of 120 people, but that's not a useful thing, right? So again, think carefully about inclusion, exclusion of things. Same thing too, right? This idea of like, oh, I'm gonna just throw everything in the bucket. And so like, these are all the things I have. I'm just gonna see what pops out. Again, shouldn't have things in there that aren't in there that are gonna create problems for sort of understanding phenomena of interest here. Inclusion of relevant predictors is theoretical issue, untestable, right? Now we can start to see indicators and things like heteroscedasticity of our heteroscedastic errors that might suggest that, hey, maybe there's something I should have in here that I haven't accounted for, but there's no thing that I can go through and test back, hey, should I have this predictor in, or do I need to have negative affectivity in this, or do I need to have hopelessness or extroversion or sort of free will or sort of whatever it is, right? This has to be a sort of conceptual issue here. And the tricky thing is if I misspecify my model, like sort of the potential impacts are complicated, could lead to biases in my estimates, my standard errors, all over the place. Okay. Again, we don't think about this a whole lot. This is a fundamental assumption of our tool. And oftentimes, just because like I have the data that I have, I just so whatever is in there is in there. That doesn't mean we shouldn't run the model, but we should probably be thinking about like what would happen if what am I missing in this model that should be in the model? And if I were to include that in the model, what would likely happen to the results that I'm seeing? Questions here? We're doing about our tools. Last assumption here, again, something that we can't test directly. Want to see expected value of error in the population 0. Basically, in OLS, average residuals for the sample are going to be 0, but this is not the same thing as sort of meeting my assumption. This is just a byproduct of the way the math works and things. Okay, but some examples of where this might sort of go wrong. Okay. Let's say I'm looking at some sort of physiological, like health-based thing, and I'm sort of measuring people on a scale because mass is sort of like relevant to my health-related outcome. If I have a scale that's 5 pounds heavy, what's going to happen is my expected value of error is not going to be equal to 0 in the population. So my expected value of my error is going to be 5 pounds heavy, right? Good news is if this happens, like your intercept is going to be biased, but that's fine. Everything shifts up a little bit, but it's not a critical issue. Okay. So this can be, and so this is often sort of where this happens, but where things can start to become a little bit more problematic. Let's say again, just we'll go back, Charlotte, because you have some interests in developmental sort of kid related things. Let's say I'm looking at playground regression, right? Number of occurrences. If I've got a group of kids who aren't smacking each other and running around and doing stuff like that, I got more reliable counts for infrequent behavior than if it's mass pandemonium and everybody's all over, like everybody's punching and kicking everybody constantly. And you got one observer trying to like mark this all down. As this increases, your reliability and validity is going to decrease. And now this is going to start to produce systematic bias and things like as those levels get more and more intense, I'm going to have more and more error. And so I'm going to have sort of differences. Like, so I'm not going to, so my errors aren't going to center around that population value of 0 things. Okay. So technically, violations here can produce biases in both my parameter estimates, my standard errors. Good news is this generally isn't sort of super serious. Generally is just impacting my intercept, which for OLS regression, we aren't always super concerned about. Generally not too big of a concern in our area outside of, I would say, just wanting to be careful about having good psychometrically sound assessments that are sort of measuring things as accurately as we can without systematic bias. It helps with our assumptions and it's going to make your results look better. It's just good thinking stuff. And when you're evaluating other people's research, okay, if someone just has a scale that they just made up, sometimes there's just not a scale for the thing that I want to measure. And so like making one up on my own is the best I can do. And then that's kind of what we're stuck with. That's better than maybe not doing the study at all. But if someone just made up a scale and there are sort of good options for them to use, then that starts to become problematic. All right. How are we feeling about this? Have a handle on our assumptions? Okay. So this is good theoretical background information. So now what we need to do is think about like, how do we go through in our data set and start to sort of go through and test some of these situations, okay? Violation of my fixed effects model is ignorable when my variables are multivariate normal, okay? And we're almost always going to violate our fixed effects assumption. So now all of a sudden we do have to be become interested and sort of attentive to multivariate normality when I'm looking at sort of my variables in my model, okay? Here we're going to assume that our data are approaching multivariate normality when each variable and all linear combination variables are normally distributed and homoscedastic. Okay, so what this is going to involve is it's going to involve us going through and looking at marginal distributions, wanting to see that our data are reasonably distributed. And when I'm going through and I'm looking at bivariate plots, that sort of those bivariate plots are homoscedastic. And if I go through and I find that my residuals are normally distributed and independent, if these two things are true, I'm going to assume that I've met reasonable expectations of multivariate normality, and that I'm probably okay to go forward without concerns about bias in my estimates. Okay. And so we'll walk through and talk about sort of what's happening here. Okay. My linearity assumptions involving normal and homoscedastic errors. We're going to look at these through some residual plots. Okay. I'm going to look at my scatter plot of my standardized predicted scores by my standardized residuals. I'm going to look at some normal probability plots. William, this is what you were looking at before, trying to go through and test things, looking at some different histograms, go through and try to see, hey, everything's kind of distributed the way we would expect. Okay. And then our concerns with independent errors, these are sort of typically associated with sort of design types of issues. Okay. Repeated measures, we know that there's going to be temporal autocorrelation, so we need to move off of a standard regression, use a different model. If we've got spatial autocorrelation, same thing. If I've got nested data structure, we're probably gonna have to use an HLM or something along those lines to better sort of parse out some of that stuff. Okay. Assumptions 5 and 6, these aren't things that we can test in the data directly, so we're just going to have to rely on sort of our own assumptions to make sure that sort of I'm reasonably and don't have massive violations. Or if I do probably have massive or have violations there, I am at least aware of them and can talk cogently about the potential impact of that. Okay. How are we feeling? Someone said, I know this is like, maybe you get a lot of, it's a lot of information sort of coming at you. Questions about any of this? You think people like, I have no clue what the words coming out of your mouth were, what the hell is going on with this? All right. Well, let's go through and sort of, and so we're going to go and jump into an actual data set here that we're going to actually start to sort of kind of look at sort of what this looks like from actual diagnostic standpoint. Okay. So our question is, we're going to ask, what are the unique associations of psychological flexibility, reward responsiveness, behavioral inhibition, and willingness to utilize social resources with perceived social support? Okay. You don't necessarily need to worry about what sort of these different variables are. So these are just psychological flexibility, sort of I talking about sort of a lack of experiential avoidance, sort of willingness to kind of lean into stuff and sort of like sort of approach situations. Reward responsiveness, am I sort of responsive to sort of positive reinforcers in my environment? Behavioral inhibition, sort of I tend towards sort of avoidance and things along these lines, and willing to utilize social, should be resources, not courses. Sort of willing to utilize sort of things in my environment in terms of social sort of needs, and how does this all play into perceptions of social support? So I've got so the MSPSS, this is my perceived social support. AAQ, this is my psychological flexibility. These things are sort of BIS-BAS scale. BAS rewards, reward sensitivity, BIS, behavioral inhibition, and then my NOS is my willingness to utilize support networks. Okay. What we're going to do is we're going to go through and we're proposing a model where Y hat, this is our model implied value of perceived social support based on a Q, BAS reward, BIS, and NOS here. Okay. And then here is my error term at the end. This is the thing we're going to focus almost all of our attention on once we get through some normality stuff on the front end. And so, verifying assumptions. Going to start off with some descriptive bivariate plots. Okay. In our screening, a lot of this is going to be the same stuff. First, we're going to go through accuracy, plausibility, right? The stuff we did last year, making sure that's underway. Look at missing values. Look at my univariate distributions, right? Here, what I'm going to start doing, remember when we're doing means-based analyses, t-tests and things along those lines, William, did we have to worry too much about our observed distributions with those? No, because the assumption was the distribution of sample means is normal, right? And that's going to happen when I have reasonably large samples or whatever I'm sampling from has a normal distribution population, okay? But now in this, because we violate that fixed effects assumption of regression, now all of a sudden our observed distributions do start to become important. So we're going to go through, take a closer look at our univariate distributions. We're going to look at our univariate outliers, and then we're going to look at linearity, homoscedasticity, and our bivariate plots. Okay. Again, thinking about our assumptions of univariate or multivariate normality, I'm assuming that my marginal distributions, my variables, are all reasonably normal, and my bivariate associations are linear and homoscedastic. So we need to go through and sort of take a look at this. We're also looking for possible specification errors, right? If I've got a relation between X and Y that's wildly heteroscedastic, it may suggest that I am missing something out of this that I need to go through and sort of make sure is in my model. Yeah. So here is my model, and this is just pulled out of state of my descriptive statistics. Any concerns here and kurtosis values, these are Stata has kurtosis value, neutral kurtosis is equal to 3. To just take these and subtract 3 to get sort of kurtosis that you would see. William, seeing any concerns with our distributions here?
I mean, I don't really know the scale of the AAQ and the NOS, but pretty big like standard deviation, so potentially highly variable, but I also don't know.
Yeah. I mean, here we're just kind of looking at one sample size. We got a good sample size? Yeah, we got a good sample size here, right? And then here skew is all less than 1. Okay, not perfect maybe, but not terrible. And then again, if we take 3, subtract all this, it's close to 0. We got there's no kurtosis value that's greater than 1. So in general, based on this, distributions are looking okay, right? We're not too worried about anything that's getting flagged here, right? Now, we've got a skew value of negative 0.9, right? And we say like, oh, that's sort of normal because it's not greater than 2. Jack, is that a normal distribution? Nope, it's sure not, right? So is this problematic in terms of like, oh, this is the worst thing in the universe? I need to immediately go through and transform? No, but if I go through and I look at this, we're very clearly seeing a negative, at least skewed distribution where we go through and we hit a ceiling here, right? And this is something to keep in mind. Here with this social support scale, 7 is the highest value you can have. We got most of our people stacked up on here. We kind of hit a ceiling effect with this. Something to take note of and start to think about, because this will start to do things to your output and do your graphs that you'll notice back, hey, that's a weird thing. Should I anticipate that on the front end? If I go through and I take a look at my AQ variable here, what am I seeing here, Jayla?
I mean, it's not normal, but it's like kind of fine.
Yeah, and we want to sort of want to, although a lot of people in this. So I got this kernel density line here that's kind of it looks maybe a little bit bimodal. Want to think about, is there something about so you got a couple of different populations in terms of my psychological flexibility, but in general, again, we don't have sort of a nice sort of normal curve here, but it's okay. Right, you got some negative kurtosis. It's a little boxy, but not anything too bad. What about Charlotte, my reward distribution here?
Kind of a negative skew, though I'm not really sure.
Yeah, so we got a little bit of negative skew, right? It's not terrible. But again, something that we sort of kind of come up at the high end of the distribution, right? So we hit another, sort of kind of a little bit of a ceiling here. Okay. Here we've got behavioral inhibition. Katie, what are we seeing with this?
A little bit negatively skewed, but kind of approaching normality. It looks
Yeah.
like a bit, maybe a little bit of binormal too.
Yeah, maybe a little bit, but really kind of the best of the ones that we've got thus far, right? So, but again, any cause for sort of major concern in terms of overall distribution? So, probably not, right? And then this is our sort of willingness to engage support networks, right? What are we seeing here, Catherine? Yeah, it's a little bit of positive kurtosis, a little peaked right here, but like at least in terms of sort of our other variables, sort of most in terms of sort of a nice distribution, right, on both sides. So doing okay, right? And so again, for your screener, what I want you to do is just sort of get accustomed to going through and interpreting sort of kind of the shape and sort of kind of going through and making sort of comments on notable features. And it doesn't have to be like a critical thing. Please don't tell me that all distributions are unremarkable. If you tell me this distribution is unremarkable, I want to flag that. That it's not like call home, but there's stuff going on there, right? So we've gone through and we've done that. What we want to do now is look at extreme values, linearity, and homoscedasticity. Again, if I'm looking at z-scores here for all of my variables, Jack, you seen anything that you're concerned about?
Negative 3.77 is quite, could be an outlier, so could negative 3.31 and 3.45. Everything else is kind of within that 3 kind of threshold. So definitely something to note, and definitely make sure to check what values they are and if they are valid.
Yeah. Here, probably not too worried. The other thing too, what's our sample size?
Really high.
55, right? And with a sample of this size, I'm actually pretty jazzed about this. We don't have anybody who's way out of balance with stuff here, right? When we get samples of this size, you're gonna have some people who are out there on the fringe. So is this something that I need to like sort of like hit the fire alarm on and like start like throwing people out? No, but I probably do want to go through and say, like, in a sample of 355, is this person who's like creeping up on 4 standard deviations from the mean gonna throw everything off? Probably not. What this person could do is this person could keep popping up as a case as we start to go through. We start looking at multivariate outliers, weird sort of leverage points and things along those lines, right? So still wanting to go through and say, things are looking okay, but here's a group of cases who we are sort of like extending out. This is what their raw score is, because again, if I'm going through and thinking about like what 4 standard deviations for the mean of social support is in this sample is going to look a lot different than what it might in a different sample. So what's the actual score? What's the standardized score, so I can get a sense for kind of where things are at with stuff. All right. Here's where we start looking at linearity, homoscedasticity stuff. All right. What I've got here is a plot of my bivariate relations, right, across all of my variables. Catherine, what we're interested in is looking for evidence of nonlinearity and evidence of heteroscedasticity. Are there any of these panels where you're starting to be like, hey, I wonder what's going on with this?
Maybe like the middle column.
Here?
Or
So we're looking at associations between sort of fast responsiveness or reward responsive AAQ and MSPSS, like these ones. I mean, these are inverses of one another. What's your concern with these panels here?
I guess one of the top one kind of is like, it's like little and then it gets bigger as you go to the right.
Looks like maybe some heteroscedasticity. Like by the time I get to this end, things are looking maybe a little bit so like thinner than sort of maybe over here. Maybe, right? Yeah, Jack, you have something to add.
I was gonna say like around like the BIS total, they just seem pretty random and there's no like form to them. No, like under, yeah, like that one and the one to the right with that diagonal right.
Oh, but
Yeah.
up here, okay, so with the BIS and NOS total, yeah.
Yeah.
What would be your concerns with these ones?
I guess I think from memory of the graphs that they seem pretty normally distributed, so I guess on further thinking about it, maybe not a problem, but they just seem a bit random and scattered all around. And there's no.
It starts to become important, right? Am I seeing a clear linear relation here? But am I seeing a different function that would fit these graphs? No, right? And so just because I have a random scatter plot like this doesn't mean I've got a violation. It's a line will fit that just as good as anything else, right? What I'm really looking for is evidence of sort of potential nonlinearity or things like that, right? So, and Catherine, to your point with these panels, I could kind of see how you might be like, well, it looks like we're seeing sort of a kind of a shape here as sort of variability gets smaller. What might be my only caveat with sort of making that interpretation based on these data here? So why might I sort of like loosen up my assumptions, sort of maybe looking at this ideas? If we're thinking about this as reward responsiveness, you think back to what that graph looked like, right? Is there much information down here? We just don't have a lot of people, right? So we could very much, we might have, and if we were to go through and fill in this, we could see reducing variability as reward responsiveness decreases. And what I also might have here is just kind of sparsely populated data. There's just not many observations out there to kind of capture. And so that might be, and if I think back to sort of my distribution of that, right, it had kind of that negative skew. Most people are kind of stacked up here in the front, which we can see. And then as we get down farther away, there's just less representation. So wanting to make sure that we don't go through and mistake sort of low levels of representation for, you know, like, oh, well, here the variability right here's just this one, and that's a lot different than this. Like, well, there's not actually variability because there's just one person there. So we want to take some of that into account. Okay. What I might go through and flag, I don't know, right? Is this, if I'm just looking at this small graph here, William, what might I hypothesize be as potentially problematic here in the relation to my MSPSS and my NOS here?
Well, one, it's clustered all in one area, but also like I mean, the NOS's willingness to utilize social networks. So like one of the things is you're kind of observing a trend that would make sense of like those who are more likely to use their social networks have more perceived social support.
Yeah. Yep, and so they're sort of looking at, yeah, there's maybe sort of a relation there, like, sort of looking at this from the 1,000 yard, sort of view. I might be like, well, we've got some, I mean, do we have problems with, homogeneity of variance, right? Because again, we don't. And recognizing, just like I said here, we've got some sparseness, but it's kind of thin up here. I might look at that back, boy, do I have some sort of like nonlinear thing going on right that, like, is that a possibility? Right, and so I might look at that and say like, within this, I wanna go through and take a look at this a little bit more closely. And so if I pull this up, this is actually sort of the opposite, this is kind of, I sort of ran this one. But if I go through and I say, okay, I wanna take a closer look at this, and now kind of zoomed in with this. Does it look like I have concerns necessarily with nonlinearity, homoscedasticity here?
I think maybe a little bit.
Maybe a little bit, but so maybe not as much. The heteroscedasticity thing starts to become sort of better here, right? When I zoom in, I'm like, okay, so I just don't have a lot of variability here, but the variability in the sort of flow I'm seeing here is not. And what we're looking at is like a 3-to-1 difference on things. So I think heteroscedasticity, I'm actually okay with once we zoom in here. And what I've done here is I've plotted both my regression line and then this is just a lowest line, right? That's sort of a curvilinear line. It'll go through and find shape. Here, I've got a little bit of a curve, but also I don't have many data points down here. And there's some stuff that's probably dragging that down. So I probably wouldn't sort of go through and interpret too much on that, right? Here, 100%, or here, I'm a bit, is there a curvilinear thing going on? Once I zoom it in, I'm thinking I'm more comfortable with this. I might also sort of like worry about like, hey, what's going on here, right? We've got kind of a big sort of like triangle looking plot right there, right? Like maybe here I'm worried about heteroscedasticity, right? So again, I pulled this one up, okay? Here's my AAQ and my VIS total here. And again, like it looks like we are, so we're hitting a floor effect here and a ceiling effect here. But as I'm sort of working through this, Catherine, am I seeing sort of something that I might identify as heteroscedastic association on the magnitude of 3-to-1 variability across things? Well, if I just sort of look at these, this is a lot sort of small, but this is just kind of the tail end of the distribution. I might kind of cut that off and not worry about that and look where I've kind of got. So here, we've maybe got less variability than here. But are we seeing something that would be close to like a 3-to-1 difference between variability at B or at AQ40 versus AQ10? No, right? So again, something that it's not perfect, but is maybe not something that's sort of reaching the point where I'm like, oh, I got to change my estimator or something along those lines. Yeah, Jayla.
I'm not understanding what you mean by a 3-to-1 difference.
3-to-1 difference. And so if I'm looking at sort of the distance between sort of my variability of scores here versus variability scores here, kind of just general rule of thumb, I would want to see sort of this variability at least 3 times bigger than sort of my narrowest here. Here is a little bit tricky because that's really sort of not much, but I also don't have, there's just not that many observations here to make a strong sort of call on things. So people kind of see what we're trying to do and sort of like what we're looking for in terms of these data. And so these are all looking reasonably okay, not perfect, but in terms of like actual real life data, it's not too bad with stuff. All right, questions? All right. Let's go through take 10. We'll take a break and then we'll jump back into regression stuff once you finish up. Okay. So note that when we're doing this, our minimum threshold, like, I don't know, like I'm not a quantitative psychologist or a statistician. But when we're going through and doing this just from applied stuff, like these are gonna over identify cases. You're gonna go through and you're gonna find lots and lots of stuff. If you don't find anything that's sort of more than 2 or 3 times the average value, sort of don't, you're good. Like, don't sort of fool around with stuff. Okay. So, for our set here, what we're gonna do is we're gonna plot these out. And again, I'm not making assumptions about the distribution of these. I'm just looking for where they fall in the distribution. So there's no normality assumption or anything along those lines. These are always gonna be skewed, okay? Jack, which one of these leverages are you gonna maybe be most concerned about?
276.
276, right? Here, if we go through, we see that we've got 9 cases with centered leverage values greater than 0.036. Again, this is 3 times P divided by the number of people in my sample, right? So this threshold will change depending on your model, right? 71, 205, 403, 256, like, it's just a lot, right? What we're gonna do is we're gonna go through and say, okay, here's what we got. These things are increasing, and then I got a huge jump, and I got that guy just kind of hanging out there on his own. Might want to go through and check this out, right? I've got eyes on all of these. I've got a recording. I sort of know kind of what's going on, because if these start popping up in other areas, I want to at least know that, yeah, they were kind of coming up in this tail, right? But like, this is the one I'm probably sort of most concerned about in this data. Questions about this? Okay. Other thing too, I will say this, and like, again, look at me. So I've worked through this in the actual, so as I'm working through an SPSS with this. Other thing we need to do is, once we identify leverage values, we need to identify why they're high leverages. Okay, it's not just like, oh, this is a multivariate outlier. We critically need to go through and figure out like what specific combination of variables is creating this as a weird case. Okay, so please never in your screening just say like, these are my high leverage values, and then leave it at that, because you're going to lose points. You need to go through and figure out like, what about these cases is creating problems. And you can have high leverage, and we talk about these as multivariate outliers, but you can have cases pop up as leverages just because you've got extreme cases on one variable. We'll go through and talk about how to sort of bend regression towards our will to start sort of seeing what's creating these or causing these to be multivariate outliers. But this is where you put on your detective cap and say, all right, I see you as problematic. I'm going to do some investigation, figure out what's going on with stuff. All right, I'm going to jump into influence. Okay. Now, high leverage, high discrepance points have the potential to impact our model, but not necessarily, right? And if just because I have a large residual, large leverage, it's not necessarily going to impact your coefficients, as we saw sort of in those graphs, right? Influence is a measure of both leverage and discrepancy. And so what this is going to do is our leverage starts to provide information on how this is going to model is going to change if we include or exclude this case in our set. What we're going to focus on, there's lots and lots and lots of different measures of influence. We're going to focus on Cook's D. Okay. What Cook's D is doing is basically going to look at the difference in coefficients for my full set of predictors with the exclusion of a targeted case. Okay. Like, if I were to go through and pull this case out, what's the change in my coefficients, right? And that sort of just a general metric of change can be reflected in your Cook's D score. Cook's D that are greater than or equal to 4 divided by sample size minus the number of predictors in your model minus 1 are things that we might sort of follow up on. Okay. Cove ratio, this is just a different measure of influence, okay? What this is doing is looking at the extent to which an observation impacts your confidence ratio or your confidence bound for a given coefficient. We're seeing what's nice about this is if you got cove ratios greater than 1, you're seeing this improves the precision of an estimate and less degrades the precision of estimate. You might say like, well, why would I care about if it's improving the estimation of my coefficient? Or wouldn't I like that, right? Well, that's that one case where you got a value that's hanging out that's sort of producing that's underestimating your standard errors because it just happens to fall exactly on your regression line. We would still maybe want to say, hey, what's going on with this case? And some benchmarks for covariance ratio. I'm not going to have you go through and do this in screening. I just want to say like, here's something, this is what it is if it comes up in other sort of areas. Okay. Going to focus primarily on Cook's distance here. Again, we're just going through like, we don't expect like a normal distribution of these. They're going to be either 0 or sort of increasingly sort of problematic. Katie, what are the cases based on Cook's distance might I be most interested in here?
276, 292,
380.
potentially 380.
Yeah, I mean, I'm just seeing these as all being sort of exceedingly far away from the rest of the distribution. And so these are some numbers that have come up previously, right? So again, you've got kind of these bad pennies that keep popping up, right? And the more they pop up, the more I might start to think about like, do I want to have this person or this case in the model? Okay. So again, we got 17 cases with a Cook's greater than 0.012, which is what the threshold would be for this model. 25, right? Are we going to go through and just like lop off 20 cases? Probably not. This is why it starts to become important to think about like, what are we doing? Why are we doing it? And not just saying, oh, these are the rules that I must follow and then sort of create a bunch of problems for myself. Okay. But I've got a set of 3 cases here that I might want to sort of take a look at. Okay. Stata does some cool stuff. SPSS might do this. I just don't know. I haven't been able to figure out how to go through and do it. But think about like, as some of you will sort of go through and sort of start playing around with R and things along those lines, there are different types of things. I really love this this drop line plot. Basically, you've got your participant number and your Cook's d value. Very clearly, you start to see in a different way than your box plot. These cases kind of standing out here, right? Just a different way to look at them, right? But something that ends up being kind of cool. Yeah. All right. So what we've done here is we rode through our leverages, our discrepancy, our influence. We're going to have a set of cases that we're then sort of going through and taking a look at and say, hey, what do I do? So who are my sort of problematic cases? What do I do with these? Some considerations there, okay? And again, remember I said that you could have 2 full semesters of regression diagnostics and still have material to go through and cover, right? We can look at sort of other aspects of linearity, sort of other measures of influence. There are ways to start looking at, I said, thinking about independent error. Typically what we do is we sort of fall back on design choices, but there are ways to go through and take a look at some stuff, right? I could have an index plot of my residuals. And let's say you've got a situation, Katie, where you all have some folks in the lab who are supposed to be doing stuff, but then you sort of, things get loose. And like what you could do is sort of run your studentized deleted residuals and have an index plot of those like over time, sort of in the order that people are collected. If you start seeing that start to get sort of increasingly large as time goes on, it could suggest drift in your researchers, like people are getting loose and loose and loose, and my data is getting more and more variable, right? So there are ways to go through and take a look. And so basically what you would see is a temporal correlation here, like errors getting larger as time goes on, which would not be great for sort of what you were doing, right? So wanting to go through and catch some of this stuff. There are things called added variable plots, where you can go through and sort of looking at, if I include this versus not, what does this do to the model and things along those lines. There's some controversy around this, and that people sort of say like this is kind of like messing with stuff a little bit, right? Like, and you sort of selecting in your data which variables to include versus exclude based on whether or not they're doing things that you like or don't, right? This isn't something that is within the tradition of psychological sciences. We work on it just because a lot of times the model's the model, because this is the model that I'm predicting to be sort of information or sort of most consistent conceptually. But in other areas, there's ways to go through and take a look at the influences, including, excluding things. And then we've got combination plots. These are cool. What we're doing with combination plots is adding certain things or sort of combinations of residuals, leverages and things along those lines to go through and start to get a sense of diagnostically what cases might be problematic. Okay. I'm going to show you these in Stata just because Stata does a better job of doing this, but you see how to do it in SPSS too. Here's a combination of a residual plot. What we've got here is your normalized squared residuals, right? And so this is a discrepancy measure, right? And here is your leverages. What we're doing is we're looking for influential cases that are large leverages and large squared residuals that are going to be out here, okay? This is a different way of looking at influence because remember that influence is a combination of discrepancy and leverage. Here we're just plotting discrepancies here, leverages here, and we're seeing like, does anything hit out in this area? This would be a high leverage combined with a high squared residual, which would suggest something that was maybe problematic, right? And here we have sort of this, we have a high leverage. It's a low residual, not a huge residual, it's bigger, but not massive. Here, we got something that's high in terms of the residual but sort of average in terms of leverage, right? So nothing really in this combination plot that sort of would suggest anything concerning. So a different combination plot. This is really cool. I like this a lot. What we've got here is we've got studentized residuals, leverages here. Then we've told Stata to create circles that are based on sort of the size of the circle is proportional to the size of Cook's D. Right? And if I look at this, what I'm looking for are things hanging out up here in the top right and the bottom right corner, right? Here I've got case 276. It's got a very large Cook's D, a very large influence value, high leverage, high studentized residual. That's someone I might want to go through and take a look at, right? So just cool ways of graphically combining sort of some of this stuff in order to sort of provide some ideas for sort of kind of where things are at. Here's what things kind of look like. I mean, you can just, from the stuff that SPSS provides, you can just say, hey, sort of plot this out. Here's my leverage by residual plot. Only thing I don't get is sort of a magnitude of influence based on this, but still I can go through and say, oh, hey, I've got this case out here that I might want to look at. I can go through and add value labels in SPSS. It turns it into kind of a hot mess, but I can at least figure out who this person is. Just note that when I do this, and I'll walk you through in the video how to go through and do this, just note that this is the position of the case in the set and not the actual person number. Okay, and hopefully you would see that this is just the 335th case in this set, probably because I had this set sorted by Cook's D and then ran this, and this is at the very bottom. So just be careful that you know that this is the appropriate case with stuff. Okay, all right. So here is me going through and identifying stuff that as I'm working through my screening, what I found in terms of usual suspects. Okay. Who here, Katie, might I be most interested in following up on and seeing maybe you consider, if I was gonna consider leaving someone out, who would it be?
6.
Yeah, 276, right? So no, not a huge residual, right? So their student residual is fine. It doesn't look like they're falling far off of my prediction line. They are predicting okay for them. But they're a strange case for some reason, right? And again, in the video, talking about how we go through and take a look at what's going on, what's causing this to be a high, a multivariate outlier. And for my cooks, they're a high influence. And when I run this combination plot, they're hanging out here. And I do want you to run combination plots, so go across both of them. And so probably what I would do in a sample of 335, this person is probably not going to completely wreck my outcome. But what I might do would, in this case, I would probably run my model with this person in there, run the model without the person in there, and see if it makes any kind of difference. If it doesn't functionally impact anything, I'll probably just leave them in, so long as their responses are valid, right? If they're someone who's screwing around, giving fake answers, not paying attention, doing weird stuff, then yeah, get them out of there. But if they are just an odd case, but they're a plausible case, I'll probably just leave it in there because I don't want to explain to someone why I'm throwing people out just for the hey ho heck of it, if it doesn't sort of change anything, right? But if this case goes through and does impact and shifts my model to any noticeable effect, they shouldn't be in there, okay? Because they're not a generalizable case, and it's having too much influence, particularly in a sample of this size, if they're going through and shifting things around, okay? Now, what's tricky ethically is this can be, it can have an impact on your model in your good way and your bad way. Best case scenario is you get rid of that person and everything changes quite a bit, and it changes in a way you like. Awesome, right? Then it's easy to go through and make the decision to kick them out, right? Because like, boy, they had high leverage and high cooks, and like this person doesn't sort of count, right? We're throwing them out. Sometimes though, when you go through and throw that person out, like the things that you like go away. That's a tough ethical case, right? No one is ever going to know, right? Because no one's going to do this deep dive of stuff, but sort of like basically you've got a model that's not going to generalize to anybody, right? Your effects are driven by one weird case that sort of exists like 3 times in the population. You got to think carefully about whether or not you have that in there. Okay. Good news is for your standard OLS regression, just a straight horse race regression where you've just got to like here what are the relevant strength of predictors. These probably aren't going to do a whole lot, right? But as we start to sort of move into moderation stuff, and we start to get interaction terms and things along those lines, then these will impact things. I've had papers where I'm getting a weird interaction. You had a paper where you got a 3-way interaction, right? People are like, oh, so those are really hard to find, right? So like kind of a pain to sort of tease apart, but like potentially interesting things along those lines. But when I went through and pulled it apart, like it didn't make any sense. I mean, the effects that it was implying didn't square with theory or like what should happen, right? It's like anxiety is good for you. Like you should probably be more anxious. It'll build resilience, right? We just reviewed a paper. I couldn't explain it. And I'm like, this doesn't make sense to me. Going back through and taking a look, it was one case. There was one case that was creating that was driving that sort of 3-way interaction. Once that person was gone, that interaction completely disappeared, right? That person can't be in that case. And then the model made a lot more sense when the one weirdo wasn't in there creating sort of a crazy thing, right? But it starts to become important, right? Because what you could do is if you were uninformed, is go through back, oh, I got this publication on sort of groundbreaking thing, like this thing actually, when you combine this and this and this way, you get this completely counterintuitive effect. No, you don't. It's a side effect of your methods, right? You didn't screen your data appropriately. You got a weirdo who's going through and creating something. It's not a generalizable thing that you should follow up on, right? So again, and you never want to get a reviewer back. You might screen your data to see if things are actually behaving the way they should, right? That makes you feel bad if that's what you get. Like also, like, did you score your data correct? Those aren't the types of comments you want to get from reviewers. Okay. All right. So, some last considerations in terms of things, multiclinearity. Again, what we start to see is the unique contribution of any given predictor will start to decrease as we start to have other predictors on there that are highly correlated with one another. Okay. Again, we did all those fun little sort of diagrams on the board. This starts to become problematic. Sort of if I go through and everybody's bringing chips to the party, no one gets credit for bringing chips to the party because no one's unique and special. Okay. What happens when I have high collinearity? Again, my regression coefficients become unreliable because my standard errors will start to get really high, right? Standard error says the sampling distribution of this coefficient is really large, which means that I would expect this to jump all over the place from replication to replication to replication. That starts to become problematic. And my regression coefficients start to get, when collinearity gets real bad, my regression coefficients get unstable. Like minor changes to the data will start throwing around my estimates of my regression coefficients. It's not good. Okay. Technically, the point estimates of my coefficients remain unbiased, but they're hard to interpret. So my standard errors will be too high. I have a regression coefficient, like standardized regression coefficient, like 0.8. It won't be statistically significant, which doesn't make any sense because that very much should, right? But we've got a problem with collinearity. Okay. Rule of thumb, you got bivariate correlations at 0.9. Like, yeah, my stuff is cool, but VIF anywhere sort of close to sort of around 2, right? If you're even close, like there's the point at which your model will fall apart, and there's the point where conceptually you need to say like, hey, does this make sense, right? Again, Cindy and Charlotte to the lab, we went through, looked at a model that was looking at sort of trying to make an argument for differences in anxiety and depression. But the measures of anxiety and depression will correlate like 0.86 with one another. Is that 0.9? No. Should they be in the same model? Starts to become questionable. For an observed variable, like you're basically measuring the same thing, you know? So if we find these, we sort of need to go through and think about, how do I trim this out? I've basically measured the same thing twice. I probably don't need to do that. Which one do I want to have in there? Regression diagnostics for SPSS, these are pretty easy. You go through and sort of just check a little box on your output. Here, this will give you your tolerance and VIF values here. So easy to go through and take a look. Again, tolerance, we're looking at values less than 0.1, VIF greater than 10. But again, asterisk, 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 if you get anywhere close to that, you're problematic. Okay. So we can go through and take a look at here. We can also, with these collinearity diagnostics, start to ferret out where I might have multiclinearity. If you just bivariate correlations, then that's easy to spot. You just look at your correlation matrix. But sometimes you can have sneaky stuff going on where you've got a combination of variables together creating a singularity, and that can be hard to figure out because individually they might not be strongly correlated, but together they're creating a perfect prediction of something. Okay. This is where your collinearity diagnostics come into play. Here, what we're looking at is a combination of things. If you've got eigenvalues that are getting close to 0 in combination with an index, condition index greater than 30, with variance proposition greater than 0.5 or 2 more variables, that's suggesting some probable stuff, right? So here, if we're looking at, and we go down, and these will sort of decrease as you go down. Here, I've got an eigenvalue of 0.004, so very close to 0. And then I've got a condition index of 33, which is more than 30. And if I go across and look, and I've got VAS reward sensitivity and NOS, it's not greater than 0.5, but these would be, it looks like there's some strong collinearity across those two, or at least some degree of collinearity. If I go through and I take a look though at VAS reward sensitivity, my VIF is, tolerance is 0.81, VIF is down here. So like, do I have problems with actually have problems with collinearity with that variable? No, right? Here NOS, tolerance is 0.76, VIF 0.13. We're fine, right? The only reason you would go down through and take a look at collinearity diagnostics down here is if you found something that was wild in your tolerance or your VIF. This is just helping you diagnose where this is coming from, if you're not seeing it by varied associations. Questions? What it looks like in Stata. So these are your things. Go through and pop it up. Just looks a little bit different. Okay, so screening summary that we're going to be working on first. Going to work through accuracy, plausibility. Okay, just like we've done before. Want to make sure everything's sort of square. Missing values. Are there missing values? Where are they coming from? What are the cases? Things along those lines. We're looking for bias in our missingness here in our mechanism. Missingness. Univariate distributions. Again, we need to have things that are reasonably distributed, because we always violate that fixed effects assumption. And we violate fixed effects assumption. Now all of a sudden our data need to be multivariate normal. So we have to go through and evaluate our distributions for that. Outliers, we're looking for problematic values here. Linearity of our bivariate relations. Here we're looking for linearity and homoscedasticity of our bivariate plots. Again, an assumption of multivariate normality. Also looking for specification error here. Again, if I see very clear heteroscedasticity in my bivariate plot, it may mean that I'm missing an important variable. Want to make sure that I have it in there. And maybe you do, right? And this will happen. You'll go through and take a look and say, I have clear heteroscedasticity in terms of my bivariate plot. Okay. But when I go through and I look at my residuals are fine. They're normally independently distributed. Everything's looking sort of normal and homoscedastic. Then you got no problem. Okay. Again, let's say I'm looking at, so going back to sort of Jack, I'm looking at the relation between age and income, right? And that bivariate plot looks terrible. But because I've got education in my regression model, when I go through and look at my residuals are just fine. Cool. That means I've got proper specification that's going in and it's counting for what's driving that heteroscedasticity. So then I'm good to go. Okay. The residuals are the end all be all. Like that's where rubber meets the road. That's where our assumptions lie. We just want to look at our bivariate stuff just to make sure that we can sort of anticipate where things might come up. Distribution of errors, we want to see normal distribution of errors, heteroscedastic errors, nonlinearity, and multivariate space, sort of things along these lines. Want to go through and take a look at that. And then discrepancies, leverage, influence, and then multicollinearity with stuff. And that, as they say, is that. How are we feeling about this? It's a lot, right? Okay. What I would recommend as you're going through and doing starting to sort of get into this, you've got videos, and I'll go through and send you the link to the specific videos. I mean, they're just in that sort of link on the main page, but I'll go through and make sure that you're pointing in the right direction with stuff. As you're working through and watching those videos, just take notes, right? And sort of process these procedures. And as you're going through, start creating your own syntax files for stuff. This is incredible. Like in Stata, like I never start from scratch with any of this. I have a do file that is labeled regression screening. And that's just what I follow every time because it's the same process every time. We're just kind of swapping out sort of variables and stuff like that. Same thing with SPSS, right? Don't start from scratch every time. Put together a good syntax file that has an annotate in there, right? Like this is what I'm doing here. This is what I'm doing here. Things along those lines. I can't tell you what a valuable resource this will be, both in this class and moving forward. If you just, I've got this. Same thing with the calculator that I keep making you build, right? Those will come in handy because you're like, oh, I don't have to go back through and pull Meng to figure out how to do this. I just have my calculator and just pop it in there and so I got it, right? We will continue to do this again and again and again. So having a nice structured file on the front end will do wonders for you. And sort of walking through and doing this with me in the video will help you loads and loads when you jump into the actual set. Because you already have it, then you're just swapping out variable names and stuff like that, right? Or you can go through and walk through, you know, sort of the pull down menus and things like that. If you prefer, completely fine. But just sort of having like, okay, this is what I'm doing and this is why, will be super helpful. Okay. Questions? Okay. What we'll plan on doing, we've got a short video, or excuse me, a short, that's the last thing, variations on regressions. This is important because it's just talking and kind of walking through sort of standard multivariate regression, stepwise regression, and then something statistical regression. We'll go through, finish up with that next week, but then the majority of class will just be sort of open lab for you to go through and work on your problem set. Okay, so in terms of thinking about due dates, we'll finish up with regression stuff next week, which will then put problem set 2 not due next Friday, but the following Friday. So 2 weeks out we've got in terms of that. But just sort of put that on your calendar in terms of sort of when that will fall. It actually, I think, should be consistently with what's on the syllabus, but just sort of double check that. Okay. Questions? We're all gonna be regression champions. Like who has the top prize for guess the correlation? Really disappointed in everybody. I have not gotten any guess the correlation scores from anybody yet. So like that's fine. You can just decide not to play, but you'll be sorry, right? Because it's a fun game, right? It's like, hey, I should be doing this thing for my advisor, but you know what? I could also do practice guessing correlations. So yeah, you can do that. It's like an Atari game. It's exciting. So all right, that's it. Thanks so much, folks. Let me know if you have questions. Please don't bang your head against the wall with this. If you're running into problems or here's what I'm saying and I don't know how to interpret it, come find me. So we'll go through and get you on the right track with stuff. All right. Thanks.
Thank you.